right, this is electron dot diagrams from noble gas notations. You want to write down everything on the paper, and I will start so pause the video and I will start here in just a minute after you pause it and write it down. Okay, we have all of this written down on our paper. We're going to write noble gas notations and do electron dot diagrams for these four elements. We're also going to mention the Aufbau principle, the Pauli exclusion principle, Hund's rule, and show a little bit about orbital notation. So with that, we start with nitrogen. First thing we're going to do is locate our element on the periodic table. So it's right there. We're going to trace backwards to the closest noble gas. So backwards, that would be helium. We're going to write that symbol for that noble gas in brackets. So we're going to go He. And then we're going to continue with the electron configuration. So after He, we go 2S1M2, and then 2P1, 2, 3. What we are doing here is following the Aufbau principle, which states that electrons fill the lowest energy level first. So we've effectively written 1s2, the lowest energy level, and they filled up that first, and then 2s2, and then 2p3. If we wanted to write the orbital notation for this configuration, we would draw a single s orbital, okay, because a s sublevel has one orbital, and then 3 orbitals for the p sublevel, because we talk about the s sublevel holding 2 electrons in its one orbital, and the p sublevel holding 6 total electrons. To an extent here, we are using the Pauli exclusion principle, which says that we can only have 2 electrons in any orbital at any one time. So underneath this orbital notation, we're going to go ahead and put the electrons in. We put 1 electron facing upward and 1 electron facing downward. Okay, this is indicating that these electrons are spinning in that orbital in opposite directions. And this in part ties into Hund's rule for these 2p3 electrons, because we have some options here on how we want to fill these electrons up. Okay, this would be incorrect. We want these electrons spaced out as far apart as possible. So if we are correctly following Hund's rule, which states that we want as many electrons as possible to be spinning in the same direction, we would put 1 electron in the first orbital, spinning upward, 1 electron in the second orbital, and 1 electron in the third orbital. So when we fill orbital notations, we always fill across a level and then across again. So if we have a p3 situation, we're going to put 1 electron in each orbital. We're not going to fill up the first orbital and then start in on the second. Let's go to potassium. So again, for the noble gas, slow down. So now we wanted to do electron dots. Okay, electron dot diagrams come from the highest numbered level of electrons, or the valence electrons. So with that in mind, we choose the second energy level. And notice the first energy level, we've effectively written 1s2 here. Okay, but we're going to use the second energy level to represent those valence electrons. So we have 2 electrons from the s sublevel and 3 from the p sublevel, so we have 5 total valence electrons. So our electron dot diagram looks like this. We have the symbol N, we go 1, 2, 3, 4, and 1 more is 5. So we effectively used the noble gas notation to draw the electron dot diagram. Now let's look at potassium. We locate our element. Potassium is element K right here. Again, we trace backward to the closest noble gas. That is argon right here. We write the symbol in brackets and we continue to write the configuration. So, okay. So we go argon, and then we go 4s1. Fourth period in the periodic table, first element in the S block. So if we wanted to write the orbital notation for that, we just draw one s orbital and we put one electron in it. Okay. Again, the off-Baugh principle, we have filled up the electrons from low energy levels to higher energy levels. Electron dots come from the valence level of electrons. Let's go ahead and write that down here. We're going to say electron dot diagrams represent valence level electrons only. So we draw our symbol, potassium, K, and we have one electron dot. So now let's go to bromine, which is element number 35 on the periodic table. Again, we trace back to the noble gas above it, so we have argon. And then we continue writing our configuration. So I'm going to try to keep this in play here if I can. So we have argon, and then we continue with our configuration 4s1 and 2. D block, and remember that the D block is one less than the row that it's in, so 3D 1 through 10. Back into P block, 4P 1, 2, 3, 4, 5. Again, by the off-Baugh principle, we are filling low energy levels first and then excessively higher energy levels as we go. Okay, we're going to do the orbital notation for this now. So an S sublevel has one orbital. A D sublevel has 5 orbitals. And remember that a P sublevel from before has 3 orbitals. Okay, now we fill in electrons by the Pauli exclusion principle that says only 2 electrons per orbital. So 4s2, we have one electron spinning clockwise, the other electron spinning counterclockwise. To fill the 3d, we follow Hund's rule, which means we want as many electrons as possible spinning in the same direction. So we go 1, 2, 3, 4, 5, and then we come back with 6, 7, 8, 9, 10. Do the same thing with the 4p with the 5 electrons in the 4p. We go 1, 2, 3, and then we come back with 4, 5. Once again, electron dot diagrams represent valence level electrons only. Valence level electrons are highest numbered principal quantum number or highest numbered energy levels. So for bromine's case, That means we are going to take these 2 electrons and these 5 electrons. Because they're in the highest numbered energy level, the 3D is actually lower numbered level. Okay, so those are not going to count. So we go 2 plus 5 and we get 7. We put our symbol bromine and we go 1, 2, 3, 4 dots, and then we start working around 5, 6, 7. Next, we find iron on our periodic table. Iron is element number 26. We trace back to the noble gas before it, so it is argon. And then we continue with the configuration. So iron is argon, and then 4 S1M2. And then 3D, 1, 2, 3, 4, 5, 6. And then if we wanted to write the orbital notation, we could. So an S sublevel has 1 orbital, a D sublevel has 5. The Pauli exclusion principle, a maximum of 2 electrons in any one orbital. Hund's rule, we want to keep as many spins in the same direction as possible. So we have 6 electrons to fill in. So we're going to fill across. So 1, 2, 3, 4, 5, and then 1 more spinning the other direction in the first orbital for 6. And now for the electron dot diagram, again we pick the highest numbered energy level. So in that case, we are looking at the 4th level. So that means iron's electron dots, okay, iron only has 2, for the most part, valence electrons. And it will behave a little bit differently at times. And this is all theory, so what we scientists think happens, but a good guess for the electron dot diagram for iron would be Fe, its symbol, with a dot above and a dot below. The other thing worth mentioning in this situation is the discussion of paired versus unpaired electrons. Okay, we can safely say that in this notation, the S sublevel electrons, this is a pair of electrons in the S sublevel, whereas the D sublevel so we're saying paired versus unpaired electrons, whereas that 3D sublevel has 1 orbital with a pair of electrons and 4 orbitals with a lone electron sitting by itself, or an unpaired electron. Okay, so that is electron dot diagrams from noble gas notations. We want to be adept at both, and we want to be aware of these definitions: Aufbau principle, Pauli exclusion principle, Hund's rule, orbital notation, and this concept of paired versus unpaired electrons.